Greetings and welcome to the complete lecture for Chapter 15 of Chemistry 223. This chapter is called Equilibria of Other Reaction Classes. We're going to look mostly in this chapter at solubility, i.e. when things form solids and why sometimes they don't. We'll also look at complex ions and different types of equilibria. So it's kind of an interesting chapter. Let's see what happens and let's get on with the presentation.
When a solution containing iodide ions is added to one containing lead 2+ ions, a precipitate of lead iodide forms. This precipitation reaction occurs because lead iodide is an insoluble ionic compound. Hydrated ions release water molecules and form the ionically bonded solid.
In Chemistry 221, we talked about solubility, and at that time, we used a solubility table, which we'll see here in a second as well, but one of the entries was for chloride, bromide, and iodide, and those three anions are usually soluble, AQ, unless they're with lead, which is what that video is about, silver, and mercury 2,2+, and we're going to come back to that. But all compounds really do have a threshold, and at that threshold, as long as you're under it, everything will continue to be aqueous. You won't see any solids. But once this threshold is reached, that's when you start to see the solids form. And with lead and iodide, it doesn't take much to see that nice yellow color of solid, which is really spectacular, by the way. It's pretty cool. So the solubility that we're going to talk a lot about in this chapter, this solubility is literally the threshold. And as long as you're under the solubility, you won't see any solid. Everything will be dissolved. On the other hand, if you get above the solubility, that's when precipitates begin to form. And a lot of the insoluble compounds we talked about in Chem 221 have very low solubility, so it's easy to overcome. But even lead 2 iodide up there, if you have low enough concentrations, you won't see any solids. So let's see what this chapter has to offer and how we can control solubility as well. This is a flashback to Chemistry 221, right around the time we did the net ionics lab, and we use this as a kind of a general rule to tell if something was aqueous, i.e. if it dissolved, or if it was insoluble, i.e. if there was a solid. We use this to figure out when compounds were solids and not. We talked about how nitrate, ammonium, sodium, potassium, these kind of things, almost always AQ. I highlighted at the time how chloride, bromide, and iodide are AQ except with silver plus mercury 2,2+, and lead 2+, and most of the negative anions, especially the polyatomic ions, are insoluble unless they're with sodium, potassium, ammonium, stuff like that. So on the right-hand side, here's like an overview and a reminder how to use this guide. Barium nitrate, if I asked if it was soluble in water, you would say soluble, because nitrate, if you look there in the upper left-hand corner, nitrate is one of the ones always AQ. There's no exceptions to the right. So we would say AQ. It dissolves really well in water. Now, barium chloride has a chloride, and most chlorides are soluble, i.e. you'd write AQ, unless the chloride, bromide, or iodide are with silver, mercury, and lead. And barium is certainly not one of those, so we would say it's AQ, it's soluble in water, and it is. On the other hand, if I asked you about barium sulfate, if it was water soluble, well, sulfates there are usually aqueous, usually soluble, but there are some exceptions, and a very notable exception is the barium. So because barium's an exception, that means BaSO4 is quite insoluble, and you wouldn't want to write BaSO4 because it doesn't dissolve really well. You'd want to write BaSO4 solid to show that it's insoluble. So these are the rules we used in Chem 221. We're now going to look at a whole new series of rules, which will still use this particular guide. However, we're going to look at much better rules here coming up. So when a chemist uses insoluble, that means that the compound does not dissolve well in water. On the other hand, soluble compounds dissolve very well in water. But you can write equilibria for all of these, even for things like sodium chloride, which is very, very water soluble. So NaCl solid can be written in an equilibrium as dissolving into Na plus aqueous plus Cl minus aqueous. Remember, the ionic compounds don't just dissolve, they dissociate into other ions. So you have 2 ions coming for every NaCl that dissolves. The solubility of sodium chloride is exceeded when the solid precipitate doesn't dissolve anymore. Remember, solubility is like a threshold, and once you go past that threshold, maybe it's like 0.1 grams, maybe it's 200 grams, who knows? But whatever that number, when you go past it, that's when you begin to form a solid. The precipitate doesn't dissolve anymore. And so even the most insoluble compounds do dissolve to a small extent. As long as you know the details of the reaction, you can make predictions.
When a small amount of sodium chloride is added to 100 grams of water, it dissolves. If we add more and more salt, eventually no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
So in that video, for that amount of water, which is roughly 100 milliliters or so, it took 35 grams of sodium chloride until you begin to see a solid. So under 35 grams, you didn't see a solid, but 35 grams or more you did. So we would say that the solubility of sodium chloride in that case is about 35 grams. But notice that we could change the volume of the solvent, water. You could add more, and that would make it dissolve. You could probably change the temperature, which you definitely could, and that would make it probably dissolve more if you increased the temperature and decrease if you decreased it, stuff like that. So all of these are factors that chemists think about when they're talking about the solubility, like what's the threshold to make a solid appear, or what's the threshold we have to go under to make the solid disappear. The silver group is 3 ions, the silver plus, the lead 2 plus, and the mercury 2 plus ions, and they all react very similar to each other. And so in this example, when you add chloride to any one of those, they all form insoluble compounds, all right? You see a precipitate. Now, they do dissolve a little bit, all right, even in the most concentrated forms, but it's pretty small. So even these insoluble compounds will have some ions over them, all right, and that's an important consideration. So these all have a threshold, a solubility, and once you go over it, that's when you see a solid. And for all 3 of these with chloride, as well as bromide and iodide, they're pretty small numbers.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
Solvent molecules, i.e. water, usually outnumber the solutes like silver and chloride ions by quite a bit. However, somehow the attraction of these two is so strong that they will find themselves, and to a pretty small extent, until they start to form the ionic solids, and that's the silver chloride that you see. So again, it's amazing that any of these compounds form, and especially when they form in such low concentrations, and that shows there's really an attraction between the cation and the anion. So once an equilibrium has been established, and that usually doesn't take too long, you can't have any more silver chloride dissolved in the solution. And this is called the saturation point, and the solution is said to be saturated. So in the little graphic down there, on the left-hand side, you don't have a lot of purple AgCl. It's unsaturated. You can add more AgCl. But you get to a point where nucleation, i.e. forming a solid, begins to occur. That points out that you are then past the point of saturation, and you're beginning to see a solid. A saturated solution is just a solution that cannot dissolve any additional solid, all right? Now, if you increase the volume, you can probably put some more in. And again, you can change the temperature even, but for that temperature and for that amount of volume, you can't dissolve any more solute. So the solubility is just literally the maximum amount of solute that can be dissolved for that volume of solvent. And solubility is usually in moles per liter, but sometimes you'll see it in grams per liter, grams per milliliter, stuff like that. Silver chloride chloride has been studied extensively, and at 25 degrees Celsius, the solubility is 1.67 times 10 to the minus 5 moles per liter. So what that's saying is that at room temperature, you can, in 1 liter of water, you can dissolve 1.67 times 10 to the minus 5 moles of silver chloride. And that's not a lot. We could figure out the moles and grams and all that kind of stuff. It's not a lot, though, however, and that's why it's easy to see the AgCl precipitate. The solubility equals the dissolved ion concentrations, because at that 1.67 times 10 to the minus 5 molar number, that's when you have silver plus and chloride ions equal to the same concentration. So when you get to that point, the silver plus and the chloride concentrations are also equal to solubility. Notice that 1 silver plus and 1 chloride came from AgCl. So if you have the solubility, the amount of moles of AgCl that dissolve per liter, that's going to equal the dissolved silver plus and the dissolved chloride concentrations at the same time. If a saturated silver chloride solution has a solubility of 1.6 times 10 to the minus 5 moles per liter, and that equals the concentration of the silver plus and the chloride, there's some kind of cool stuff we can do here. You can calculate an equilibrium constant K based on this reaction. Now, notice the form of this equilibrium constant. The solid is the reactant, for example, AgCl, and the ions that go into it are the products, i.e. silver plus and chloride. So remembering that solids and liquids never go on the equilibrium expressions, the K value would be the silver plus concentration times the chloride concentration divided by 1. Don't include the solids and liquids. And each silver plus and chloride are both equal to 1.6 times 10 to the minus 5. So it's like solubility squared, 1.67 times 10 to the minus 5 times 1.67 times 10 to the minus 5, which comes out to be 2.79 times 10 to the minus 10th. And this type of equilibrium constant gets a fancy name. It's called KSP. It's the solubility product constant. This equilibrium constant arose because it was the product, i.e. we multiplied the solubilities by each other. So KSP is the product of solubility, the solubility product constant. And that's what we're going to talk about a lot this quarter. So if you're talking about KSP, the solid precipitate will always be your reactant, and then the ions that go into it will be your products. And that's how all of these KSP systems are set up. Notice that the KSP value is less than 1. Less than 1 for an equilibrium constant means you have more reactant than product. That means we're going to have more solid, undissolved solid, than we will have the ions. This is definitely a reactant favored K. That's why the solid is preferred over these ions in general.
When solid lead chloride is added to water, a small number of ions are released into solution. Those ions can reattach to the solid, while other ions can dissolve. A state of dynamic equilibrium is reached, in which the concentrations of ions are constant and can be described by an equilibrium constant expression.
This is the equilibrium constant expression for lead-2 chloride. So PbCl2 solid is the reactant, and lead-2 plus and 2-chloride ions would be the products. The KSP for this reaction is quite well known. It's 1.9 times 10 to the minus 5. And how they got that, KSP here would equal the lead-2 plus concentration times the chloride ion concentration squared, since there's 2 of them, and you would divide by 1 because there's nothing in the reactant side. Don't include solids and liquids. Here's some representative KSPs of different values, and none of these are the numbers you have to use. We're going to do a lab in Chem 223 where we're going to use that calcium hydroxide KSP. So keep that in the back of your mind. That might come in handy. But all of these KSPs are less than 1. That shows that they're all very insoluble in water. This question asks, which of the following correctly displays the equation used to describe the KSP for barium fluoride? Barium fluoride dissolved in water, which is basically what all of these are going to be, by the way. But anyway, in a KSP expression, the solid is the reactant, and the ions that go into it are the products. So the first one has barium fluoride solid. Barium is positive 2, fluoride's negative 1, so you need 2 of them to balance the barium. It would be insoluble, so you'd write an S next next to it. So I like the reactant part of A, but the product is incorrect. That just shows dissolved barium fluoride, and honestly, that's not what we're after. We want the dissolved ions. So if you look at B, that's getting warmer. You've got a barium 2 plus ion, but fluoride ions are F minus, and they don't like to be next to each other. So I don't know what that F2 minus thing is, and that's kind of weird. However, answer C has the solid barium fluoride, digging it, and the ions that go into it would be barium 2 plus ions, AQ, plus 2 fluorides, AQ. I'm liking that. So answer C looks like a really good answer. D doesn't have the right stoichiometry or the right formula for that matter. Barium is positive 2, fluorides minus 1. That wouldn't be a correct formula. And the last one is basically the opposite of a KSP. Everything's flipped. The solid is the product, the ions are the reactants. Don't use that. So again, KSPs, the solids will be the reactant, and the ions that go into it will be the products. Now, solubility and KSP are different numbers, and that's really important to point out here. Solubility is usually expressed as the mass or moles of solute dissolved in a liter or 100 milliliters or something like that, all right? It's usually for us, it'll be moles per liter, but it can be expressed different ways. So solubility is a molarity, and KSP is the product of solubility. So, for example, in that one problem, we took the solubility and multiplied it by itself, the silver plus times the, I think it was chloride, to get the KSP value. So KSP and soluble are different. So on the right-hand side there, we've got lead 2 iodide dissolving in water. So the KSP expression would have the solid as the reactant. The ions that go into it are products. And we can use the solubility to calculate KSP. The solubility here, 1.30 times 10 to the minus 3 moles per liter. And again, what that's saying is that for every liter of water, you should be able to dissolve 1.30 times 10 to the minus 3 moles lead 2 iodide. But you go over that, you'll see a solid, stay under it, and you should see everything dissolve. Solubility, X, is how much PbI2 breaks down. And for every soluble X that breaks down, you're going to have another X of lead 2 plus, like it's a 1-to-1 ratio, and you'll have 2X, or twice that amount, for the iodide. So the solubility is the moles per liter of lead 2 iodide that break up. And for every PbI2, you're going to have 1 mole of lead. So the same number can be used for the lead 2 plus concentration. However, the iodide will be twice that number. There are 2 iodides for every lead, 2 iodides for every PbI2. So we'll multiply that number by 2 in order to find the concentration of the iodide. So iodide would be 2.60 times 10 to the minus 3. Anyway, you put those two numbers together. We want to calculate KSP. So you've got the lead is 1.30 times 10 to the minus 3. The iodide is twice that number, 2.60 times 10 to the minus 3. You can throw this all together. You want to square the iodide because it's iodide squared. KSP 8.79 times 10 to the minus 9. So the solubility here was 1.30 times 10 to the minus 3, and the KSP 8.79 times 10 to the minus 9. Quite different numbers. KSP and solubility are different. So in this question, the solubility of barium sulfate is found to be 1.05 times 10 to the minus 5. What's the KSP value? Okay, so first we need to figure out what the KSP expression is going to look like. Now, barium sulfate is BaSO4, and it is quite insoluble. However, like all insoluble things, it is soluble to a certain extent. So the equilibrium would have BaSO4 on the reactant side, and on the product side, you'd have barium 2 plus ions, and you'd have sulfate ions, SO4 2 minus. Now, for every barium sulfate that breaks down, you're going to have 1 barium ion and 1 sulfate ion. And why that's important then is that the concentration of the barium 2 plus ion, as well as the concentration of the sulfate ion, will be equal to the solubility. So since KSP is the product of solubility, we'll take the barium times the sulfate. We'll take the 1.05 times 10 to the minus 5 number and use it for barium, and then multiply it by the same number for sulfate because it's the same compound, 1.10 times 10 to the minus 10. So again, KSP equals barium times sulfate equals X times X. If you use solubility, that sometimes is seen as X. So if you square X, You are good to go. In these kind of problems, it's very common for a chemist who wishes to make a precipitate of an ion, all right? If you make a precipitate, you can filter the solution with a piece of filter paper, and the solids will be extracted from the liquid, and you can remove them. And if they're dangerous, for example, that can be kind of important. So if you have, for example, in this problem, mercury, maybe you want to get rid of the mercury, which is probably not a bad idea. So let's say that somewhere, maybe in your grandfather's basement or whatever, you find a 0.010 molar mercury 2,2 plus solution. Now, why that was in your grandfather's basement, no clue at all, but just go with it, okay? Anyway, let's say we want to get rid of the mercury. We want to remove the mercury from the water. Well, we can use the fact that this mercury 2,2 plus ion is quite insoluble in the presence of chloride, and it makes the wild Hg2Cl2 solid there pretty readily. The KSP is very small, 1.1 times 10 to the minus 18th, so we know it's very reactant favored. And so if we add just like a little bit of chloride, it should be able to make a precipitate of this weird Hg2Cl2. And again, once you have the solid, you can use filter paper to filter it out, and we can get rid of this nasty mercury. So what we'd like to know in this first part, how much chloride can we add in solution without forming Hg2Cl2? Like, what is the threshold chloride amount that's needed to just begin precipitation of this solid? So we want to know if we need to have like kilograms, or can we add micrograms? That's the kind of question that this kind of thing would answer. It's not too hard to figure out. So we're going to use the fact that the KSP 1.1 times 10 to the minus 18th equals the mercury ion concentration times the chloride ion concentration squared. And our mercury concentration is apparently 0.010. So if you put that 0.010 up for the mercury, you're going to solve for chloride ion. We'll take the square root to get rid of the chloride squared thing. Chloride's going to be the square root of KSP over our mercury concentration. So putting this all together, the KSP 1.1 times 10 to the minus 18th divided by the mercury concentration, which is 0.010. And to find just the chloride, we'll take the square root of it, since there's 2 chlorides per Hg2Cl2. This comes out to be 1.0 times 10 to the minus 8th molar. And that is very, very small. And what that tells you is that it's not going to take a lot of chloride to make a Hg2Cl2 begin to precipitate. And that's kind of cool. Now, chloride isn't usually a very hard ion to come across. It's available, of course, in table salt, NaCl. You can use it in hydrochloric acid. That would be a source of chloride. Lots and lots of sources of chloride. And this number says it certainly isn't going to take very much. 10 to the minus 8th is really small. It's not going to take very much chloride to make that begin to precipitate. So we've decided we're going to go for it. We're going to raise the chloride level now to 1.0 moles per liter. And again, initially the mercury concentration 0.010. So we want to know how much mercury is going to be left in solution when the chloride has been raised to 1.0 moles per liter. And again, chloride is so cheap in terms of NaCl, hydrochloric acid, whatever, it shouldn't be too hard to do this. How much mercury is left? And that's a totally fair question. Well, it's back to the KSP expression for us. In this case, KSP equals mercury times chloride squared, but we want to solve for mercury. We want to know how much is left. So the mercury is going to be the KSP divided by the chloride ion squared. Well, KSP is still 1.1 times 10 to the minus 18th. Divided that by the chloride concentration, which is 1.0 and 1.0 squared. And lo and behold, the mercury is now 1.1 times 10 to the minus 18 moles per liter. That is small. Now, chemists will like to collectively pat themselves on the back because you started with a roughly 10 to the minus 2 molar mercury, and we went to a 10 to the minus 18 molar mercury. So that's about 16 orders of magnitude that it's dropped, and that is considerable. That's a lot of mercury being lost. So in this case, we have gotten rid of a lot of the mercury. But you'll notice I didn't say all of the mercury. You do still have 10 to the minus 18th moles per liter. Now that's hardly a lot. It doesn't seem like it would be very much, but maybe your system is really sensitive to mercury. So just realize we'll talk here about separating metal ions and stuff like that, but it's not a complete separation. There's always going to be a few atoms running around. So even though we went orders of magnitude smaller, it's not a complete separation. Keep that in the back of your mind, especially if you have a really sensitive reaction. But at the end of the day, I would pat myself on the back because an order change of 10 to the 16th, that's huge, all right? That's a huge, huge amount. So yeah, pretty cool. However, if you're really sensitive to mercury, whatever system you're looking at, maybe 10 to the minus 18th is still too big, and you might have to add another chemical to make that value of the mercury 2,2 plus go down even more. So just think about that in the back of your mind. So here's a reaction with strontium carbonate, and we want to know the concentration of carbonate required to begin precipitation of insoluble strontium carbonate from a solution containing 0.050 molar strontium 2 plus ions. Okay, so here's the big picture. We must have found now in my other grandfather's basement, if you will, a 0.050 molar strontium solution. And again, why they'd have a strontium solution, I don't know. However, we realize that strontium carbonate has a small KSP, 5.6 times 10 to the minus 10th. So if we start adding carbonate in, we can begin the precipitation of strontium carbonate. We can filter out then the solid and lower the strontium concentration down. Well, anyway, in this problem, we'll use the fact that KSP equals strontium times carbonate, the strontium ion times the carbonate ion. And we have there the concentration of the strontium ion. We just want to essentially solve for carbonate. So what this looks like, KSP equals strontium times carbonate. Carbonate is what we want to solve for. Carbonate is going to equal KSP divided by the strontium ion concentration. And it comes out to be 1.1 times 10 to the minus 8th moles per liter. So again, a very small amount of carbonate will be needed to begin precipitation of strontium carbonate. And if we push that carbonate level a little higher, we'll start to lower that strontium level quite considerably. The common ion effect is used sometimes to explain how to get rid of one particular bad ion, if you will. And in the process of getting rid of the bad ion, you end up adding something else, and we'll talk about that here in a little bit. But in this picture down here on the bottom, we're talking about silver acetate. Silver acetate is somewhat insoluble. You can see in the little test tubes there that there's the white solid on the bottom, and that's silver acetate. But there is more acetate in the solution over the solid, and we'd like to get rid of it. So what we're going to do here is we're going to add silver nitrate to the solution. So we're adding silver. Silver is an ion common to the equilibrium that we're studying. And as you add silver ion, silver reacts with acetate even more, pushing it to the reactant side, which in this case is insoluble silver acetate. So you can see in the right-hand picture there's even more silver acetate in solution. On the far right picture, you can see there's only one little red acetate above the solid. So that's trying to show that there's less free acetate than there was before. However, by adding an ion like this, we're adding in another species. So we're adding nitrate from silver nitrate. So at the end now, nitrate is running around. It kind of takes the place, if you will, of the acetates that formed a solid. And that's another consideration to realize. You can't have something for nothing usually. We're adding silver nitrate. A lot of the acetates go into the solid, but we do end up then with nitrate in the solution, which can be a problem or it can be something cool. Depends on what you need to do.
In the test tube is a solution containing lead ions. To this we add a solution containing chloride ions, and lead chloride precipitates. Solid lead chloride is in equilibrium with lead ions and chloride ions in solution. At this point, we add more chloride ions in the form of a sodium chloride solution, which disturbs the equilibrium. More lead chloride precipitates, which removes still more lead ions from solution.
This video shows what happens when you have lead 2 plus and you want to get it out of solution. You want to precipitate it out as PbCl2, lead 2 chloride. All right. So in the far left-hand column there, both in the top and the bottom, you can see there's a yellow line for the lead 2 plus concentration. That's how much lead 2 plus is in solution. And we have on the top no green PbCl2. But the first red dashed line, that's when we're adding some chloride. It's probably sodium chloride or something like that. We're not usually too concerned about the counterion, but it is something to consider. But anyway, adding the chloride then, the chloride begins to act with the lead 2 plus to make PbCl2. So on the top graph, a first little green line appears. It kind of maxes out after a while. That's because the lead and the chloride are reacting to make a solid. So in the lower graph then, you can see chloride starts kind of high and goes down because a lot of the chloride is used to make the green line above the PbCl2. But most importantly, our lead 2 plus concentration does go down, but it doesn't go down perhaps as much as we'd like. So the second red dashed line, we're going to add another chloride addition. Again, another source of sodium chloride or whatever. And you can see in the top part there, the green line gets even higher. That's because we're making more PbCl2. And in the bottom down there, you can see how the lead 2 plus concentration is certainly decreased. All right, it's gone down a lot. It's not zero like we talked about. Hopefully this is a level we're happy with, but it is something to be considered. You never totally get rid of these things, but you can wipe them out by several orders of magnitude. So this is the common ion effect. You're probably adding sodium chloride to make the PbCl2 crash out, make it precipitate, and in the process then you are left with chloride and then some kind of counterion, for example, sodium and sodium chloride. So let's calculate the solubility of barium sulfate in pure water and in the presence of some barium ion. Now, barium nitrate is a compound that's very soluble in water. All nitrates are soluble. It'll break down into barium 2 plus and nitrates. It's the barium 2 plus we're going to be interested here in B. So for the first part, KSP equals 1.1 times 10 to the minus 10 for this reaction. And notice that KSP equals barium times sulfate. All right. So in pure water, we're just going to calculate the solubility. Solubility will equal the barium 2 plus. It'll also equal the sulfate. So what we'll do is we'll let X equals the barium ion concentration and the sulfate ion concentration. So KSP equals X times X or X squared. We'll solve for X and we're good to go. But for the second part, we're going to have some barium already present. Now, think back to Le Chatelier's principle. If you were to add a product like the barium 2 plus ion, by Le Chatelier's principle, that should make this reaction go to the reactant side, i.e. shift to the left. And what that's going to do is that's going to lower the solubility of the barium sulfate. Because if you start adding barium, there's like too much barium. The barium will react to a point with sulfate and make more barium sulfate, but the solubility will go down. So when we do the barium ion, we expect the solubility to be less than what it was in pure water. So let's check this out. So we're going to first look at A, which is just the pure water example. The solubility equals X, which equals both the barium ion concentration and the sulfate. So it's like KSP equals X times X or X squared. And if you want to solve for the solubility, which is what X is, square root of KSP, 1.0 times 10 to the minus 5. So in a liter of water, you can dissolve 1.0 times 10 to the minus 5 moles. That's in pure water. Now in part B, we're going to have some barium ion already present. And again, by Le Chatelier's, you start adding the barium ion in, that's going to shift the reaction to the reactant side. Solubility, which is what we're measuring, should be less, all right? The barium is going to make the solubility go down. So we can test this out and see. Now we expect, like I said, the solubility to go down, all right? Adding an ion common to the reaction, i.e. the barium nitrate is adding a barium ion. That should make the reaction take a left, i.e. shift to the reactant side. That's what old Le Chatelier's principle would say. So we expect then in the presence of the barium ion, the solubility should be less. So let's check this out. Same KSP equals barium times sulfate, etc., etc. But the difference now, if you want to set up a full ice table, is that we have some barium already present, 0.010. Now, solubility has to be a positive number, and solubility will be the same as the sulfate. So I used a Y here instead of an X, but you could use X if you want to. So notice that at equilibrium, you'll have the barium plus some amount Y, and sulfate will be just Y. So if you use those equilibrium values and you set it equal to the KSP, which is 1.1 times 10 to the minus 10, you can solve for the solubility Y. Now, as default, this would be a quadratic formula. You'd have Y squared plus 0.010Y minus KSP equals 0, and you can go crazy. But however, in the last example, the solubility was pretty small, 1.0 times 10 to the minus 5. And we just predicted that in the presence of barium, the solubility Y should be an even smaller number. So probably it is quite all right by sig figs to ignore the plus Y for barium. So barium will end up being just 0.010. You don't need to worry about that plus Y. It's going to be incredibly small. Remember with sig figs, when you add and subtract, it's always about the doubtful digit. So 0.010, that last zero is at the thousandths place. And 1.0 times 10 to the minus 5 has a lot more zeros in it. It's not even going to affect the small amount that it's going to create. So, make a long story short, ignore the plus Y. So it's going to end up being just 0.010 for barium, still have the Y for sulfate, that's with the solubility, and when you solve for it, 1.1 times 10 to the minus 8. That's the solubility in the presence of the barium ion. Now again, it was 1.0 times 10 to the minus 5. Now it's 1.1 times 10 to the minus 8th. So solubility has certainly decreased. It went from 10 to the minus 5 to 10 to the minus 8th in the presence of the barium ion. So this is another example of how Le Chatelier's principle can still help us out. It's a real powerful tool. It's helping us to figure out the directions of the solubility, helps us make sense of our answers and stuff. Le Chatelier's is pretty awesome. This is a question you might run into. It's a will a precipitate form question. All right, and how these work is you usually have a concentration of the cation and a concentration of the anion, and it says will a precipitate form. To answer these questions, you will need the KSP for the compound you're looking at. So in this case, it's strontium chromate, SrCrO4, and it's 2.2 times 10 to the minus 5, not real big. That equals the strontium ion concentration times the chromate ion concentration. So what you can do to figure these out, there's a couple different ways, but what I usually do is I use a Q versus K comparison. My Q will look just like K. It'll be the strontium ion times the chromate, and I'll compare my Q to the KSP this time. If the Q is less than KSP, that means no solid forms. But if Q is greater than KSP, then that means a precipitate has happened. So there's all the different variants you can get into. If Q equals K, the solution is at solubility, there's no precipitate, and that's honestly pretty rare. Most of the time Q will be less than K, so there's no precipitate, and then after you get to the right point, Q will be greater than K, and a precipitate forms. So we're going to use the 0.010 for the strontium, we'll use the 0.010 for the chromate, and see how this works out. So in this problem, I'm going to multiply those together and calculate Q. Q comes out to be 1.5 times 10 to the minus 4. And remember, KSP over here, 2.2 times 10 to the minus 5. Well, 10 to the minus 4 is bigger than 10 to the minus 5. Q is greater than K. So that means a precipitate forms. Strontium chromate has been made. And that's kind of a cool thing to know.
In the test tube is an aqueous solution containing ions of silver, lead, and copper. When we add chloride ions, a precipitation occurs, producing solid silver chloride and solid lead chloride. The copper ions remain in solution, indicated by the blue color of the liquid, which is decanted. We add distilled water to the test tube and heat it. Lead chloride is soluble in hot water and returns to solution. We again decant the solution in the test tube, leaving solid silver chloride. To demonstrate that the decanted solution contains lead ions, we can add chromate ions, which cause the precipitation of lead chromate. The characteristic yellow color of the precipitate confirms the presence of lead. We have separated the 3 ions in the original solution from each other.
This is a pretty cool video. You have a solution which is a mixture of copper 2+, silver plus, and lead 2+. And the goal is to separate and to a point identify that you have those individual metals separated into different test tubes. And it's pretty cool. So what they do is they first add a chloride, and silver plus and lead 2+, as we've said, react with chloride as well as bromide and iodide, and the mercury 2,2+ will do this too. But anyway, they all make insoluble compounds. But copper 2 chloride, would not form under these conditions. Most of the time, chloride, bromide, and iodide are soluble. They won't form solids, and that's what happens. So once the solids are made, they decant the solution, which means gently pour off the liquid and keep the solid in the test tube to the best of your ability. So that's how they get the copper 2+ away from the silver and the lead. All right, copper 2+ doesn't form a compound with the chloride. So now they've got to separate the silver and the lead from each other. And what they do here is a temperature dependence. Lead 2 chloride is more soluble at warm temperature than silver chloride is. So they separate the solutions in the heat. It doesn't look like much. It looks like some of the white solid goes away. But that's enough to tell you then that the lead chloride should have been separated. So again, they decant. The lead goes into the solution side, and the silver chloride remains at the bottom. So the silver chloride now has been officially broken away from the other ones. Now, you're getting rid of the liquid. You're decanting the liquid from the silver, but do you really know you have lead? And that's a very fair question to ask. So at the end there, they added a chromate source. Lead 2 chromate makes a really cool yellow color. And in this case, as you can see, you absolutely have it. So the original test tube ended up with just the copper because it didn't react with chlorine. They then used temperature difference to separate the silver from the lead. The white compound in the middle is silver chloride. And then finally, they thought they had lead chloride, but you never can be sure. So they added some chromate. The chromate reacted with the lead, and it made the insoluble PbCrO4. So it's kind of a cool thing. This is how chemists think about separating matter from the wild. Let's pretend that we have a 0.020 molar silver plus and a 0.020 molar lead 2+. And what we want to do is we want to add chromate to both this combined solution. And we're going to know what we add because if you make silver chromate, Ag2CrO4, it's kind of a red color. And if you make lead 2 chromate, PbCrO4, it's kind of a yellow color. So we want to know what color are we going to see first, which precipitate will form first. And to answer all of this, we need to have KSPs. So we have 2 KSPs here, one for silver chromate, one for silver chromate, and one for lead chromate. And you can see, first of all, that the lead chromate number is smaller, 10 to the minus 14th, than the silver chromate is. Hint, hint, we'll come back to that. Now, the KSP for silver 1 chromate is going to equal silver plus times chromate. And for lead 2 chromate, that's going to equal lead 2 plus times the chromate ion, and that'll also be important. Now again, in this problem, we've got this much silver and this much lead. We can use all these informations to calculate how much chromate is required by each ion. And whatever number we get, all right, we're going to look for the smallest amount of chromate because the smallest amount of chromate will reflect on the one that precipitates out first. So it's kind of a cool thing. It's mathematically not very hard. It can be a little confusing, but it's nothing you can't do. So for the silver chromate, when you want to find the chromate, that's going to equal the KSP divided by the silver ion squared. And you can see that number there comes out to be 2.3 times 10 to the minus 8th moles per liter. And that's an important number we'll come back to here in a little bit. But it doesn't seem to be a very big number, so that's kind of neat. However, if you do the lead chromate, you end up with a chromate concentration of 9.0 times 10 to the minus 13th. And that number is much, much smaller than 2.3 1.3 times 10 to the minus 8th. So the smaller amount of chromate will precipitate first. That means that the PbCrO4 will precipitate out. As a general hint for these kind of problems, if you go back and look at the KSP, assuming the concentrations of the ions are pretty close to each other, like they're both 0.020 in this problem, almost always the smaller KSP will be the one to precipitate first. So you can see there's 10 to the minus 14th for lead-2 chromate. On the other hand, silver chromate, 10 to the minus 12. So almost always smaller KSP will be the first to precipitate, and that's what we're seeing here. That's not 100%, but it's much more often than it isn't. In this problem, we have a solution that contains both sulfite, 0.10 moles per liter, and sulfate, 0.30 moles per liter. And we're slowly adding a calcium compound into the solution. And the question is, what precipitates first, calcium sulfite or calcium sulfate? And it gives the values for the KSPs. Now, most of the time, like I said, smaller KSP will be the first one to precipitate. So you can see there that the calcium sulfite, 1.3 times 10 to the minus 8th, calcium sulfate is 10 to the minus 5, quite a bit bigger. So we would predict here, based on those numbers, calcium sulfite's probably the way to go. But wait a minute, I don't believe you, Dr. Russell. Oh, good question, random student in the back of the room. This is kind of a hand-waving way to say that, oh yeah, smaller KSP first to precipitate out. But what if you really want to make sure? All right, and that's a very fair question. So what you want to do in this case then is you want to solve for the calcium ion concentration. So both of these, KSP is going to equal the calcium times either sulfite or sulfate, depending on what you have. So if you want to solve for the calcium, which is what I did here in the answer, it's going to be the KSP divided by the ion. So the sulfite here is 0.10. That gives you the concentration of the calcium needed to make calcium sulfite. And then if you do the same thing for the calcium sulfate, the KSP for that divided by 0.30, the concentration of calcium, 8.0 times 10 to the minus 5. And you can see 1.3 times 10 to the minus 7th is a smaller number than 8.0 times 10 to the minus 5. It's going to be pretty chill for the calcium sulfite to be made. And this just proves your point as to what exactly to expect.